Sir Isaac Newton gave us the formalism that is the backbone of classical mechanics. He first gives us in the first law, the so-called law of inertia, a definition for what is meant by force. And that definition is keyed in to the alteration of motion. The alteration of motion being the acceleration. It'll be a point of interest for us later on that Isaac Newton rarely talked about acceleration, but was more interested in the quantity of motion, which was an idea that we now call momentum, that we'll be studying a little bit later in our physics. But what Isaac Newton did for us is he provided us with the now famous second law. The second law says that the net force, the sum of all of the forces acting, is equal to the mass of an object multiplied by the acceleration. That is to say, that when an object is subject to some force, the alteration of its motion in the form of the acceleration will be in proportion to the quantity of inertia that the object has, which is measured by the mass, and will be in the direction of the net force. There are some subtleties to this. This law, when you get into it and start to sort of a kind of cowboy physics, you start applying this law to the solution of problems and you just start calling it F equals ma without thinking in detail about the subtleties of what the notation means. So I'll just go through that very quickly to say that what I have here is the net force, sigma F. What that means is that in any given physical situation that I'm trying to solve, the physical system that I'm interested in might be subject to more than one force. And the law implies, brace yourself for this, erroneously, the law implies that the object reacts to the sum total of all the forces. Notice there's a harpoon on the force. That means the vector sum. And in our introduction to the course, we talked about how to find the vector sum of forces. So what Newton implies is that the total force is the cause of the accelerated motion. That is almost always the case. That the acceleration of the system is caused by a linear superposition of forces. It is almost always the case. It is not always the case. It is not always the case. This is what we call a linear law, in that it depends on the superposition of forces, or that the total force can be written as a linear superposition of forces. There are physical systems for which this is not true. They're so-called nonlinear systems. They're a branch of physics known as chaos or nonlinear dynamics. I'm hoping for an opportunity to speak about that more later on. But for our purposes in our physics, I can find the sum total of all of the forces that act, and then I'll find that the direction of that net force is exactly the direction of the acceleration that results, and that acceleration is in proportion to the mass. So it's a very straightforward law. We're quite fortunate, in fact, that it is easy to solve. The difficult part is not applying Newton's second law to problems necessarily, but in fact identifying the influences that affect the system. I keep saying the system, and I'm trying to consciously say the system as opposed to the object, because what I mean here is that I'm going to look at a physical situation. I'm going to identify the object or objects whose motion I want to understand. But an object can be compound. That is, it can have multiple parts. For example, you might say, what are the forces that influence Shidley's motion now moving around in front of the room? Well, a Shidley is a Shidley taken in whole, but also it's a head, arms, legs, different parts that can move independently. When I apply Newton's second law to a system, I want to make sure that I apply it to a group of objects whose acceleration is the same. If I have a compound object and the acceleration of every part of the object is the same, then I apply Newton's second law to the object as if it were one unit, one system. But if I have an object where components of the object have different accelerations, then I have to treat those individual objects with separate applications of Newton's second law, if you will. So there's a limitation that actually turns into a strategy I'll describe in a moment. Another thing that I have to keep in mind when I apply Newton's second law is that it applies only in reference frames that are moving at constant speed with respect to each other. Here's what I mean. I could sit still here in the laboratory and build an apparatus, some sort of experimental thing where there are some marbles that go back and forth and some strings that pull and forces are exerted, and I theoretically predict what the accelerations will be, and then I experimentally measure what the experiments will be, and I find that Newton's second law holds perfectly lovely here in my little experimental apparatus. You build identically the same experimental apparatus, but instead of building it here in the laboratory, you build it on a train that is moving down perfectly, beautifully smooth tracks at a constant speed. speed. When you do the experiment in that reference frame that is moving with a velocity v relative to my reference frame, I fully expect that the Newton's second law will apply in that reference frame as well. Such reference frames where Newton's second law applies equally are called inertial reference frames. We run into a problem, though, when we do experiments in reference frames that are accelerating relative to one another. Quick example. Imagine here in the laboratory I build a support with a string and a mass hangs from the string, and then I observe it according to Newton's second law. It's quite a simple problem. The force of gravity is acting down on the thing, the tension in the string is acting upward, the net force acting on it is equal to zero. It does not accelerate, it simply, and Newton's second law applies. You build the same apparatus, but instead you build it, I've actually done this, it's a fun thing to do and it freaks everyone out on the airplane, is you bring yourself a mass on a string onto the airplane, and you hold it up while you're sitting in your seat waiting, and as the airplane begins to accelerate down the runway, the mass, pendulum bob if you will, deflects from its vertical position because of the acceleration. Now if I observe that according to Newton's second law, and I draw all the forces involved, it's quite strange in fact, because I look at it and say, well, there must be some influence that causes the bob to deflect from its otherwise vertical orientation, that there must be a new force. Now, of course, you realize you have a very sensible understanding that the new thing that has been introduced is the motion of the airplane, because you can hear the roar of the engines and you feel the rumble as it goes down, and a little queasy feeling as your innards move around this way and that way. You understand that something's happening. But strictly by the application of Newton's second law, it's a curious thing, and you add a force in your frame of reference that does not exist in my frame of reference. Such a force is sometimes called a fictitious force or a pseudo force. They're forces that result when you apply Newton's second law in a reference frame that is accelerating. That's a no-no. Newton's second law does not apply in reference frames that are accelerating. It's okay, though, as long as you're aware of that, you can compensate for it. And it's important that we be able to do that, because as I stand on the surface of the Earth, I have a velocity due to the Earth's rotation, and because the Earth rotates, I'm going around in a big circle. And so my velocity vector is constantly changing direction. That change in velocity vector for me is an acceleration, and so right now, I am accelerating. Unlike being on the airplane, I don't feel the influence of that acceleration, because the acceleration is in fact quite small. The alteration of my velocity is small because the radius of the Earth is so large, and I don't feel it, but I can observe it in two very distinct ways I think we're all familiar with. If we go to the Franklin Institute in the city, they have an enormous pendulum there, right? It's like 8 stories high pendulum, enormous. I love a pendulum. I don't know, there's something aesthetically pleasing to me that the pendulum, a lot of motion happens. Like, we get very excited about like roller coaster motion and motion of bullets and things like that. Things that are exciting happen at high velocity. I'm also thrilled by the thing that happens at very low velocity in the pendulum, very chill. Now, according to Newton's second law, if I observe it right there, standing in the stairwell at the Franklin Institute, I should have a pendulum that swings back and forth in a straight line. There's some viscous drag involved, but at some point, I guess some munchkins come running out from somewhere and give it a push, and then they go hide again. It should swing back and forth in a straight line, but that's not what happens. What happens is the pendulum is deflected from its otherwise planar motion. And so if you observe that with Newton's second law, you want to explain that, as we'll talk about or describe later, as angular acceleration. You want to explain that angular acceleration, the deflection of the pendulum, in the context of some force, a force that does not exist. The pendulum is deflecting from its otherwise planar motion because of the rotation of the Earth. There is a fictitious force, because it's all of our physics that we do, even the physics I do here in the laboratory, is in a non-inertial reference frame, because I'm in a reference frame that's accelerating. That force, as you know, is called the Coriolis force. The Coriolis force is not a real force. It's fictitious. It doesn't actually exist. It's an artifact of Newton's second law due to the rotation of the Earth. And we see it also in hurricanes. Hurricanes rotate as they travel. Well, it's a hurricane in the northern hemisphere. In the southern hemisphere, it is a typhoon. Yeah, I think it's a typhoon in the southern hemisphere. So we live in the northern hemisphere. Let's consider that. So the hurricane rotates in the northern hemisphere counterclockwise, right? Counterclockwise rotation counterclockwise in the northern hemisphere. And so if I look at that from an atmospheric dynamics point of view, I might go, well, why? Because all it is it's warm air rising, cold air falling. Why isn't a hurricane, I suppose you could say, radially symmetric? There must be some force that is the cause of the rotation. Well, that force is fictitious. The Earth is rotating. And so the Coriolis force in that case is also an artifact of applying Newton's second law in non-inertial reference frames. So it has limitations, and we'll want to take care that we never make the mistake of applying Newton's second law in a reference frame that's accelerating. But since our first step whenever we're solving any physics problem is to choose the reference frame, all I need to do as the physicist is to make a smart choice and not make that mistake. It should be easy enough to do. So here I have Newton's second law, and the trick is that, I want to talk about this other thing about the system. There is a classic problem of physics that appears very often on our exam and in our physics, and that is when I have a compound object made of two parts, I've already alluded to. Here I have an object that has a mass, shall I choose some numbers here? No, I'm not going to choose some numbers. I'm going to call this mass M1, and then right next to it is another mass M2. And this mass M2, I've drawn it smaller if they're made of the same material. Presumably, it's a lighter mass. It's a smaller mass, but it's not necessary for my discussion. And perhaps they're sitting on some sort of surface where there's no frictional influence. I don't want to worry about the frictional influence here. It'll confuse what I'm saying. And I immediately despise this diagram, and so I'm going to redraw it exactly the way that it was, but I'm going to draw it and it makes me happy, because it turns out that for this discussion, my haps is fairly critical success. All right. So I have a mass M1, and I have a mass M2, and here they are. I can look at this two ways. I can look at it as two masses, M1 and M2, where the total mass is M1 plus M2, or I can look at it as one mass, whose total mass is M1 plus M2. I'm impressing upon you this. I can only treat them as a single mass together if they have the same acceleration. And they will in the circumstance that I'm describing here, because what I'm going to do is apply a force to M1. You see over here, there's some influence. I don't know what it is. It's probably just me pushing with my hand or something like that. And there's the force F, and I push on M1. Let me be very clear. The force acts on M1 only. It does not act on M2. It is a common mistake made by students of physics to take that force F and apply it to M1 and also to M2. That is not true. M2 moves under the influence of forces that are directly incident upon it, not forces that it has a casual acquaintance with through another object. So I have to be careful about that. But I can apply Newton's second law to this situation by saying the net force that acts, which in this case, I'll just say, I'll be a little bit explicit about it, that the net force, the sum of all the forces, is simply equal to the force F. The fact that I'm solving a simple problem, I shouldn't let that train me to be careless about the application of Newton's second law. So I have just that force acting, and that force is acting upon the total mass, M2 plus M1, because I'm telling you that when we observe the acceleration, M1 and M2 accelerate together as if they're one object. M1 and M2 accelerate together as if they're one object. So the result of this is that I can understand in the context of Newton's second law that the amount of acceleration that I'm going to get is simply going to be the force per unit mass, the amount of force that is applied here, divided by the total mass, which is M2 plus M1. And so I can calculate what that number is, the acceleration, for both objects together. I can only do this, again, impressing upon you, I can only do this because I'm saying that they have the same acceleration. Now, once I've done that, I'm at liberty to apply Newton's second law again, because the fact of the matter is, in the context of problem solving, I can apply Newton's law to any object that I choose. Any object that I choose. I just point to it, define that object, and if I can identify all the forces that influence the motion of that object, I'm off to the races. It's the only requirement. So I'm going to apply Newton's second law now to M2 as well. Well, now M2 is subject to a different force. What is the force that is actually the cause of 2's motion? It is not the force capital F. It's the force of M1 pushing on M2 by virtue of the fact that they're in contact. Shall I call that a normal force? I'll call that a normal force of contact, and so I'll say when I write, I'll make a note here that I applied this to the total mass. I don't know how to, darn it, M2 plus M1, as I applied that to. And then down here, applying it simply to M2, the net force that acts on M2 is in fact simply the normal force. I use a capital N here, and many textbooks use a lowercase n. I find that a little bit vulgar, but then someone would make an argument that using capital N for normal force is a bad idea because the unit of force itself, the Newton, is a capital N. Well, then I can have an equation that says, n is equal to 5n, and it might be confusing for anyone who doesn't realize the difference between units and forces. So here's n, the normal force, would be equal to only the mass m2 multiplied by the acceleration. But what acceleration? If m1 and m2 together have an acceleration of a, then m2's acceleration is a. So it's the same acceleration that I determined before. It's the same acceleration that I determined in the first part. And so, in fact, I could show that this is a fraction of this. I'm going to write it out. It's going to be unsightly, but it's going to be m2 divided by m1 plus m2 multiplied by, pardon me, I lost my mind for a second. F. No, look what it says. That the force that is exerted on m2 is a fraction of the force that was initially applied to m1. Some people like to think, I hate this. Some people like to think that force is exerted on m2 and the force is exerted on m1, and that part of the force is absorbed by m1, and that the leftover force is exerted on m2. I don't like this because it makes it seem like forces are a thing, that forces are real. I was having a conversation yesterday, pretty crazy conversation, about whether or not forces actually exist. Right? It makes it. You see how it makes it seem like the force is oozing through the first block, and then whatever's left up, because that's not a real thing, right? That's not a real thing. What it is behavior that I'm describing here. And so this concept is so useful in problem solving, and for the first time ever, I've never really done it this way in terms of my order of talking about Newton's second law, but as I said, I'm just making this stuff up anyways, so there you go. That's going to be a really useful idea going forward. Now, once I've defined my physical law here, and I realized this part when I was saying let the normal force be capital N and it confuses with the units. Now that I've written my physical law, I can look at the right-hand side of this physical law and discover from it what the units of what I expect the units of force to be. Because F is equal to the inertia in the form of the mass multiplied by the acceleration, then naturally the mass has units of kilograms in our physics, and we multiply by the acceleration, which naturally has units of meters per second squared. And so combining those units, naturally, force is going to have units of kilogram meters per second squared, which does not roll trippingly off the tongue, but is a very sensible unit because I know the equation is quite simple. So knowing the units is simple to do. But we give this a simpler name, obviously, in honor of this accomplishment of Isaac Newton. And we call that capital N, the Newton of force. Here in the United States, of course, we're very familiar with measuring forces in pounds. Our own weights, for example, we describe in terms of pounds, and you're going to find that a Newton is much smaller than a pound. So, for example, your physics professor weighs somewhere around 1,200 newtons, which sounds like a sad thing, but these are quite smaller than pounds, and so you'll have to become accustomed to that in order to interpret whether your answers are correct. This has been just sort of a summary of Newton's second law and the things that I have to watch out for, how it works. There is no substitute for solving lots and lots of problems using Newton's second law. Newton wasn't finished with this because there was another law. Oh, by the way, just a little bit of an aside with both of these things that are up for discussion today. Always remember that physics is an experimental science. So when Newton writes Newton's second law, we don't immediately accept it. It's just something dreamed up off the top. It's certainly a very reasonable argument, but it's just dreamed up off the top of the head, and only after long experimentation does it become solidified. And so there are aspects of it where you might think about it and go, why would Newton do that? Well, Newton was very clever, and experimentation since then has borne out that, in fact, this is reliable. Newton's second law does not always apply to every physical system that there is. Some of you know that I have a background in quantum mechanics, and that's my bag. There is no Newton's second law in quantum mechanics. In fact, Newton's second law is wrong when it comes to describing the behavior of subatomic things or atomic scale things like atoms, for example, the hydrogen atom. If I try to apply Newton's second law to the hydrogen atom, it's not just inadequate, it fails utterly. It makes incorrect prediction of the behavior of atoms. So Newton's second law certainly is the underpinning of our classical mechanics, but it is not the end-all be-all of physics. It's simply appropriate for what we're trying to do.